For the first example problem for relative motion of two particles using translating axis, we have here a train travels at a constant speed of 60 miles per hour, crosses over a road as shown in the figure below. If the automobile A is traveling at 45 miles per hour along the road, what we need to determine are the magnitude and direction of the velocity of the train relative to the automobile. So here, as shown on the right side, are the answers. So the magnitude of the velocity, that is 42.5 miles per hour, and the direction is 48.5 degrees clockwise. So just a solution for this problem, before we determine the velocity, the magnitude and direction of the velocity of the train relative to the automobile, we need to establish or identify the reference frames. So we need to have two reference frames for this problem. So the first reference frame refers as the fixed reference frame, and the second reference frame is your translating reference frame. So here in our problem, having an axis XY, this would be your fixed reference frame. So this will be your basis of your origin. So this is where the fixed observer is located. So this is your basis of your position vectors from the origin to your particles train and also to your automobile. And the second reference frame, which is your translating axis, which defines with x prime and y prime, is located, or it is located to or moving with the automobile A. So here, this is your translating axis, where this automobile is your translating observer. So from the fixed origin, we can determine the velocity vectors to automobile and train. So from the fixed origin going to your train, it is denoted with v sub t. And from the fixed origin going to your automobile, that will be denoted with the velocity vector v sub a. And from the translating axis, which is located onto your automobile, this vector will be denoted as your velocity of the train relative to A. So here, we had a triangle, so we can apply vector addition for this one. So by applying or by using vector analysis, so that would be the velocity vector of the train is equal to the velocity vector of the automobile plus the velocity vector of the train relative to A. So since what we need to determine here is the magnitude and the direction of the velocity of the train relative to the automobile, what we need to do is we will transpose or rearrange the equation that is equivalent to your velocity of the train relative to A. So this equation will become v of t relative to A is equal to v of t minus v of A. And take note, this equation is in vector form. So before we determine the magnitude and direction, we make sure that the given must be in vector forms. So for velocity vector of the train, that would be equal to 60I miles per hour. 60 miles per hour, it's because, as you can see here in our illustration, the train is moving along the x-axis. Okay, so just a recap of the unit vectors. If this is our three-dimensional, this would be your x, y, and z. So x refers as your I, y is your j, and z is your k unit vector. So since this is a two-dimensional, so we are using two axes only, which are the x and y. And here in our problem, the train is moving along the x-axis based from your fixed reference frame. So your vector form of the velocity of your train would be equal to 60I miles per hour. Now for your velocity vector of the automobile, that would be equal to the x component plus the y component. So as you can see in the figure, since the velocity of your automobile is, if I will draw again the coordinate system, if this is your y prime and x prime, and this is the velocity of your automobile. So for us to write that into vector form, we will determine first the x and y components. So for that, we have here its x component and also the y component. And here, the angle from the horizontal or from the x-axis, that would be equal to 45 degrees. So 45 degrees is this one. So that's why that is 45 degrees. Your 45 degrees is from the horizontal axis or your x-axis. So from that, the velocity vector form or your vector form of your velocity of your automobile would be equal to VA cosine 45 degrees, since the x component is adjacent to your angle 45 degrees, and the y component would be sine 45 degrees because your angle 45 degrees is opposite to your y component of your v sub a. So this would be your equivalent of your VAX and VAY. And for that, since we have a given velocity of your automobile that is equal to 45 miles per hour, so we will just substitute here in our equation. So that will become 45 times cosine 45 degrees I plus 45 sine 45 degrees J. So for that, the velocity vector form of your v sub a would be equal to 31.82I plus 31.82J miles per hour. So since we already converted, or we already know the vector form of your velocity of the train and also the velocity of your automobile, we can now substitute that on your equation for us to determine the velocity of the train relative to the automobile. So that was v sub t relative to A is equal to v sub t minus v sub A. So v sub t, that was 60i, minus v sub A is equal to 31.82i plus 31.82j. So from that, we can distribute the negative. So this would become 60i minus 31.82i minus 31.82j. So we just combine the like terms. So here we just combine the 60i and the negative 31.82i, and this will become 28.18i, since 60 minus 31.82 is 28.18i minus 31.82j miles per hour. So this is the vector form of the velocity of the train relative to A. Since what we need to know is the magnitude, so by using the Pythagorean theorem, the magnitude of the train relative to the automobile is equal to the square root of your x component, which is the 28.18 squared, plus the y component, which is the negative 31.82 squared. So therefore, the magnitude would be equal to 42.50 miles per hour. So this is your magnitude of your train relative to the automobile. Afterwards, once you determine the magnitude, you can now determine the direction. So for the direction, if we draw the velocity of your train relative to the automobile in a coordinate system, so the x component is acting along the positive x, since it is equal to positive 28.18 miles per hour, and the y component is acting along the negative y-axis because it is equal to negative 31.81. 31.82 rather, miles per hour. So this is your velocity of your train relative to the automobile, which is equal to 42.50 miles per hour. So the direction that we need to determine here is from the horizontal or from the x-axis. So this is your angle that we need to determine, which refers to as a direction. And we will denote that with theta v. And from that, we can use trigonometric functions to determine the angle theta v. So that would be tangent theta v is equal to adjacent over the opposite over the adjacent rather, because tangent of any angle is equal to the opposite over the adjacent. So the opposite of your angle theta v is your y component. So that will be v sub y. And the adjacent side is the x component, which is represented by v sub x. And for that, for us to determine the tangent, make sure to use the absolute value. And we can substitute the X and Y components. So Y component is negative 31.82 and the X component would be 28.18 miles per hour. So for that, the negative 31.82 over 28.18 is equal to 1.129. And since it is it has an absolute value for the answer of your negative 31.82 over 28.18, so it becomes a positive. And from that, we use inverse tangent to determine the angle theta v. So your angle theta v would be equal to 48.47 degrees, and that would be in a clockwise direction. So that will be your direction of the velocity of the train relative to the automobile. So that is how we determine the relative motion of two particles using translating axis.